Okay, in this video we're going to be looking at position, velocity and acceleration in terms of vectors and the principles of kinematics and how they apply to vector calculus. So the main difference with vector calculus, kinematics, is that we have both magnitude and direction, but the basic principles apply for vectors as they have previously. So if we find the dot product between a vector A and a vector B, we just multiply our I components together and multiply our j components together, our y in this case, and we end up with our x values multiplied together and our y values multiplied together. We don't when we dot them, we make sure that we don't expand, because ax times by, because that's in the I direction and that's in the j direction, we know if we have two vectors and one's in the I direction and one's in the j direction, the angle between them is 90 degrees. We know that a dot b is equal to mod a mod b cosine of the angle between them. If that angle's 90, cos of 90 is 0, so a dot b will equal 0. So if we find the dot product of these two things, they will just be 0. So we know it's just the I components multiplied and the j components multiplied. Or we could say x and y in terms of vectors, position vectors, time-varying vectors. Okay, so the magnitude or length of a vector, A is given by the vector dotted with itself and square rooted. So all we're doing is we've got our x component dotted with itself plus our y component dotted with itself and then square rooted, which is ax squared and then ay squared and square rooted. The scalar dot product of two vectors a and b is related to their respective magnitudes and the angle between their tails. So if you've got two vectors and the angle between them, we can work out the dot product, or we can work out the angle between them. Two non-zero vectors are perpendicular when their dot product is 0, and we just went through that up here. If the angle is 90 degrees between them, it will equal 0. Okay, if we're given a position vector, generally a position vector will be given to you as r of t. So consider a particle that moves along the line a to d. The position at any time is given by the vector r of t. At time t, the particle is at the point b, i.e. r of t. Then the particle moves to the point c, which is r of big T plus the change in time. So here, if this was 2 seconds, and then this one here comes 2 seconds later, this would be r of my initial value, 2, r of 2, that's big T, and then plus my change in time, which is 2, so that would be r of 4. So we've moved from here, B, to C. Our displacement is from here to here. We know that we've gone from r of big T plus the change in time minus our initial position. That will tell us what our displacement is from where we started. So in this case here, from B to C, if we want to work out displacement, it's our final position minus our initial position. So, which is the difference between the final position, t plus our change in time, so if it's been another 2 seconds, and its initial position, which is r of t. Okay, the distance from the origin of a particle at any time. So if I want to work out what this distance here is, it is just we need to put in the time that we want it to occur. So if I wanted, scrub this out to make it nice. If I wanted my distance from the origin, so from here to here, I've got to find r of big T. If I want to find the magnitude of this vector, we just dot the vector with itself and square root it. So that will dot my I components together and add my j components dotted together, and then that will give us, when I square root it, that'll give us the length of that vector, which is the distance from the origin to that point. Okay, find the distance from the origin of the body described by the position vector r equals 2ti plus t squared minus 1j minus 5k at t equals 2. So we just need to find first r of 2, which we know is going to be 4i plus 4 squared, 2 squared, sorry, 4 minus 1, 3j, I don't know why I put that bracket there, and minus 5k. Now if I want to find the magnitude of this vector, or the distance, I want r of 2, which is the vector dotted with itself. Now I'm going to use square root 4, 3, negative 5, dotted with 4, 3, negative 5, which we know is the square root of 16 plus 9 plus 25, which is the square root of 50, which is 5 root 2. Okay, so that's the distance from the origin to the position vector r of 2. So the distance from OO to the position vector given by 4i plus 3j minus 5k. So it's the distance from the origin to this particle or body when it equals 2 seconds. Okay, now we know what the average velocity is. It's the change in displacement over the change in time. So we know our change in displacement is our final displacement minus our initial displacement, and our change in time over our change in time. So that's our average velocity. It's not instantaneous, it's average. So it's change in displacement over change in time. Okay, find the average velocity of the body with position vector r is given by root t plus 1i minus t squared on 3j plus 5k between t equals 0 and t equals 3. Okay, so we'll say r initial is, when I put 0 into this, I get I 0j and then plus 5k. Then r final, when I put 3 into it, I get 2i. What was on the bottom of that? When I put 3 into that, I get 9 on 3, which is negative 3j. And then when I put 3 into that, it stays the same. So this thing is going to stay at the same height, 5k. Okay, so our average velocity is our final 2i minus 3j plus 5k minus our initial, got to put a bracket around it because we're minusing the whole thing, plus 5k on our change in time, which is 3 minus 0. So our velocity average is, okay, so I've got 2i minus I, which is I, minus 3j minus nothing, so minus 3j, 5k minus 5k, which is 0, on 3. So my average velocity for the first 3 seconds for the first 3 seconds is 1/3 I minus 3j. It doesn't say what it is, but generally it'll be meters per second. So in this case here, we can't really give anything. But remember, it is a vector. It's not, if it was speed, it wouldn't have direction, but this has direction because it's a vector. Okay, now we want instantaneous velocity. Basically, instantaneous velocity, we just need to differentiate each component, our x component or our I component. We need to differentiate with respect to t, and likewise for our j component. So here, if I want my instantaneous velocity, it's the limit as the change in t approaches 0, because that makes sense. If we've got a position vector and another position vector, if I make the change here in time approach 0, they're going to be right next to each other, and it's going to give me my gradient of my position vector, which is my velocity. Okay, so I've said here dr dt is dxi dt and dyj dt. Dx dt, we know that when we've got a position vector, our I component is x of t, and our y component, our y of t is our j, our y component. So we just derive them independently, our I component and our j component with respect to t. Now generally we say v of t is equal to r dot of t. So that means the first derivative. So that'll be dx dt I plus dy dt j. Speed is a scalar quantity, so once we find, or if we've got our velocity vector, we dot it with itself and then square root it, so we find the magnitude of it, and that will give us our speed, remembering that it is a scalar product, a scalar quantity, so it doesn't have direction. And when you dot them together, that'll get rid of any vectors that you have existing in the vector. It'll make it become scalar. Okay, so an object has a position vector in meters. R of t is that function there. Find the velocity vector, v of t. So luckily we know r dot of t is equal to v of t. Get used to that because I use both in the exams. So we know if we derive this, we're going to get 6t. When I derive sine, I get cos, but I've got to bring my coefficient out. So pi cos pi t I plus, now I'm going to derive this first. I'm going to get 2, because when I derive this, I get negative e to the negative t j. Okay, so that's my velocity vector at any time. From here, we need to find our velocity of our object when t equals 2. So we want to find r dot of 2. Now if I put 2 into this function, v of 2, that should be a 2. Okay, so we get 12 minus cos of 2 pi is 1, and I've got minus pi, so I get 12 minus pi I plus, when I put 2 into this, I get 2 minus e to the negative 2 j. And of course, that's our answer. we don't have to do anything else because our velocity has direction, which in this case is 12 minus pi in the I direction and 2 minus e to the negative 2j, which is in the y direction. Okay, next we want to find our speed. And we know that our speed is our magnitude of our velocity. So, when we dot our I component with itself, we'll get 12 minus pi squared. When we dot our j component with itself, we'll get 2 minus e to the negative 2 squared, which if we put into our calculator, so 12 minus pi squared, let's go back. Okay, so we want the square root of 12 minus pi all squared plus the 2 minus e to the negative 2 squared, 9.05. Okay, and it's in meters and seconds, so 9.05 meters per second. We really should have, it should have stated to 2 decimal places or something. If it hasn't, then that would be our speed, because we can't calculate it. Okay, the average velocity in the first 2 seconds of the body's motion. Not forgetting that our average velocity is our change in displacement over time. So, our initial position or our position when t equals 0, so I'll say r of 0 is 3 times 0, and then sine pi times 0, which is 0. I get 0i, then I get e to the negative 0, which is going to be 1, plus 2t, 2 times 0, which is, we're just going to get j. That's my initial position for this vector. Now, we're going to call it final in this case, is at 2. So I get 3 times 2 squared, which is 12. If I put 2 into here, sine of 2 pi is 0. So I get 12i, and then plus e to the negative 2 plus 4j. And now we want to find our average velocity. So velocity, oops. So v of is our final velocity, 12i plus e to the negative 2 plus 4j minus our initial position, which is j, all on our change in time, which is 2. So our v of is, what have we got, 12i on 2, which is 6i. Then I have e to the negative 2 plus 4 minus 1. So I'm going to say plus 1 on 2e to the 2 plus 3 on 2j. So that is my average velocity over the first 2 seconds. Okay, so we found a displacement at 0, a displacement at 2 seconds. We do r final minus r initial over my change in time, and that gives us our average velocity. Our instantaneous velocity is of course just our derivative with respect to t for each component. Okay, now our acceleration is, our average acceleration is our change in velocity over time. So average acceleration, change in velocity, so my v final, we'll call that v final, minus v initial over the time that's occurred. So that's if you want the average. You don't use the acceleration, you use the velocity vector. If you want your instantaneous acceleration, likewise, like as we did before, we derive each component with respect to t. So find the acceleration vector for an object who is given by. So r of t is e to the 2t I minus 2t cubed plus tj plus t log e t k. Okay, this one seems like it's going to be fun. R dot of t is 2e to the 2t I, so we derive that, minus 3t squared plus 1 j. This last one we're going to have to use a product rule, so plus, I'll leave the t alone, so t, and then I'll derive log et, which is times 1 on t, plus, derive the t, we get 1 times log et, k. Okay, so let's clean it up a little bit. 2e to the 2t I minus 3t squared plus 1 j plus t times 1 on t is 1 plus log e of t k. So that is my velocity at any time. Now if I want my acceleration, we can say r double dot, because we've derived it twice with respect to t. Okay, so I get 4e to the 2t I minus, that's going to disappear, so I end up with 6t j plus, when I derive 1 I get 0, log e of t, I get 1 on t k. So, assuming I haven't stuffed anything up, our acceleration is given by a of t is equal to 4e to the 2t I minus 6t j plus 1 over t k. For, in this case it would be t is greater than 0, because we couldn't sub t equals 0 into the acceleration vector for all t greater than 0. Okay, a body moves in such a way that its position vector in meters at an instant t seconds is given by r of t is that. Find the velocity vector, so we know v of t is equal to r dot of t. I like to remind us of that because in exams, generally they give it as r dot as opposed to v of t. Okay, so if we derive this first equation, we end up with 15 minus t I. We end up with 12 minus t squared j. Our acceleration vector, we know a of t is given by r double dot of t, which is, when we derive that, I get negative I minus 2t j. Okay, from here, let's see, find the angle between the velocity vector and the acceleration vector at the time t equals 1 second to the nearest degree. Okay, so I've got to find the direction of the velocity vector when t equals 1. So v of 1 is equal to 14i, and then plus 11j. A of 1 is negative I minus 2j. Now, if I want to find the angle between these two vectors, we know v1 dotted with a1 is equal to the modulus of a the modulus of v1, I should say, the modulus of a1 cosine of the angle between them. So we can say theta is equal to cos inverse of v1 dotted with a1 over mod v1 mod a1. Okay, we know mod v1 is equal to the square root of 14 squared plus 11 squared. 196 plus 121 is root 317. Okay, a1 magnitude is 1 squared plus 2 squared, which is root 5. So we've got our bottoms. What is v1 dotted with a1? 14i times negative 1 is negative 14, plus 11 times negative 2 is, so minus 14 minus 22, which is minus 36. Okay, so we've got cos theta, or theta is equal to cos inverse of negative 36 on root 317 times root 5. Okay, put our calculator in degrees. Cos inverse of, what do we have? We had negative 36 on root 317 times 5. 154.72. I think it's to the nearest degree. 154.72. Therefore, 155 degrees to the nearest degree. Okay, what's our last? The time when the body has an acceleration of magnitude 9.8 meters per second. Acceleration magnitude. Okay, so magnitude means the size of acceleration. So our acceleration is given by negative I minus 2t, that's not a vector, j. So our magnitude of acceleration is given by the square root of negative 1 squared plus negative 2t squared, which is the square root of 1 plus 4t squared. And we want to know when that is 9.8 meters per second squared. So we say root 1 plus 4t squared equals 9.8. If we square both sides, we get 1 plus 4t squared is equal to 9.8 squared. We get t squared is equal to 9.8 squared minus 1, on 4. T will then equal plus or minus the square root of 9.8 squared minus 1 on 4. As t is greater than 0, t equals 9.8 minus 1 squared on 4. .8 squared, oops, I forgot the 2, minus 1 on 4. 4.87 seconds. Therefore, when t equals 4.87 seconds, we have acceleration magnitude 9.8 meters per second squared. Okay, so we've gone through instantaneous position, we've got position vector, our displacement versus distance, our velocity versus average velocity versus instantaneous velocity versus speed, acceleration, average acceleration, instant acceleration.